I am Pavitra, Department of Mathematics, working in Erode Secondary Engineering College. Today we are going to discuss about that apply linear algebra. What is mean by linear algebra? Linear algebra is one of the important branch of mathematics, and linear algebra is basically the study of vectors and linear function. And this paper in our college studying in Entech CSE department in second semester paper. Under this topic we are going to discuss about that. First unit is system of linear equation, second unit is vector space, third unit is linear transformation, fourth unit is inner product space, fifth unit is application of eigenvalue and eigenvector. In 5 units we can first discuss about that vector space. We already know that vector space is direction. So application of vector space is the direction of a vectors specify the line of actions of the force and the magnitude specify how are the force. For example, a vector include the position, acceleration, electric field, etc. So next one is topic of vector space. The first topic is vector space, second topic is subspace, third topic is linear, dependent and independent, fourth topic is basis and dimension, fifth topic is null space, sixth one is a dimension theorem. First 4 topic is an important 7 mark question and the definition is 2 mark question. The fifth topic is a null space. Here includes the column space, R of t, n of t, etc. The sixth topic is dimension theorem. So here state and prove the dimension theorem is an important 7 mark question. So next we can discuss about that definition of vector space. A vector space V over a field F consisting of a set on which two operations, addition and multiplication, are defined so that for each pair of elements x, y belongs to V, there is a unique element x plus y belongs to V, and for each element A in F and each element x in V, there is a unique element Ax in V, such that the following conditions are holds. So clearly you can note that can image V is a vector space over a field F and x and y belongs to two elements in V. So clearly you can note that V is a vector space over a field F. Yes, you can take x and y belongs to V. Can do operation addition and multiplication. Here x plus y belongs to also in V and A in belongs to F. So here A dot x belongs to also in V. Can clearly understand? You can image x and y belongs to V. Can two operations x plus y belongs to also V. Yes, and A belongs to an F, x dot A belongs to also in V. Satisfies this condition and also the following conditions are holds. The first condition is x, y belongs to V such that x plus y is equal to y plus x is a commutative law. The second one, for all x, y belongs to V such that x plus y of plus z equal to x plus of y plus z is an additive associative law. The third one, for all x belongs to y and 0 belongs to V. So he can clearly note that the third condition is x belongs to V and 0 belongs to V such that x plus y of x plus 0 is equal to x and 0 plus x equal to x is an additive identity law. The fourth one is x, minus x belongs to V such that x plus of minus x equal to 0 or minus x plus x equal to 0 is an additive inverse law. Then fifth one is for all x belongs to v, comma 1 belongs to v, such that 1 dot x equal to x or x dot 1 is equal to x is an multiplication identity. Sixth law is for all a comma b belongs to f and x belongs to v such that a comma b of x is equal to a of bx. Multiplication associative law. The seventh condition is for all a comma a belongs to f and x comma y belongs to v such that a of x plus y is equal to ax plus ay. Left distribution law. The last condition is for all a comma b belongs to f and x comma x belongs to v such that a plus of x is equal to ax plus a bx is right distribution law. For the above result, the set of satisfies the above 8 conditions. The given elements are vector space. The first condition is x and y belongs to v. Second condition is we have having the addition and multiplication two operations, and third one is x plus y belongs to v, and fourth one is x dot ax belongs to v, and also satisfies the 8 laws: commutative law, additive law, associative law, additive inverse law, additive identity law, multiplication identity, multiplication associative law, left distribution law. The last one is right distribution law. So next we can going to see that problems. Let V be the set of all matrix M cross N with the real entries. Only the elements are real entries. Let F be a field of rational numbers. Let us define Aij plus Bij is equal to A plus Ij. For all A comma B belongs to M matrix of M cross N numbers in a field and C belongs to F. Also C of Aij is equal to C Aij. Prove that V is a vector space over a field F. In this problem you can clearly note that the first one, V is a vector space. It having the matrix A matrix, B and C. The matrix or satisfies the following 8 conditions, means that given matrix or vector space. Clearly note that V is a vector space. The vector space having 4 matrix. The 4 matrix or satisfies the 8 conditions it means that V is a vector space over a field F. Okay. Solution. Let capital A is equal to Aij of matrix M cross N. Capital B is equal to Bij of M cross N. Capital C is equal to Cij of M cross N, since Aij, Bij, Cij belongs to capital F. The first condition for all x comma y belongs to V, such that x plus y is equal to y plus x. So here a plus b is equal to Aij M cross N plus Bij M cross N. So here x is equal to capital A and y is equal to capital B. So you can substitute the matrix value Aij of M cross N plus Bij of M cross N. So adding this two matrix Aij plus Bij of M cross N. So in adding process means that we already known that 2 plus 3 is equal to 5 and 3 plus 2 is equal to 5. So this means that B plus A is equal to Bij of M cross N plus Aij of M cross N. So Bij of A plus Ij in M cross N and Bij of M cross N plus Aij of M cross N. So it means that A plus B is equal to B plus A. Hence prove that commutative law. The second condition for all x comma y comma z belongs to V, such that x plus y of plus z equal to x plus of y plus z. So a plus b plus of c is equal to, here capital A is equal to aij m cross n plus bij of m cross n of plus cij of m cross. Can first adding this two matrix aij plus bij of m cross n plus cij of m cross n. So his two terms of adding terms. So aij plus bij plus cij of m cross n. So you can split this matrix aij of m cross n plus of bij of m cross n plus cij of m cross n. So next step is aij of m cross n plus of bij plus cij of m cross n. So here capital A plus b plus c. Hence to prove that a plus of b plus c is equal to a plus of b plus c. So I can note that. So hence to prove that additive associative law. The third condition, for all x belongs to V and 0 belongs to V, such that x plus 0 is equal to 0 plus x is equal to x. So prove that a plus 0 is equal to capital aij of m cross n plus 0 matrix is zeros of m cross n. So that adding this two matrix aij plus 0 of m cross n. So any numbers you can adding to 0, get the value is same the number. So capital A. So similarly 0 plus A is equal to A. So hence to prove that additive identity law. So the fourth condition, for all x comma minus x belongs to V, such that x plus of minus x equal to 0 and minus x plus x is equal to 0. We can take minus a is equal to minus aij of m cross n. Okay, so now a plus minus a is equal to aij of m cross n plus minus aij m cross n, which is equal to aij minus aij. So the value is equal to a plus minus a is equal to 0. Similarly, minus a plus a is equal to 0. So hence to prove that additive inverse law. Fifth condition, for all one belongs to V and x belongs to V, such that 1 dot x is equal to x or x dot 1 is equal to x. Now 1 dot a is equal to 1 dot aij m cross n. So multiple with 1 into any number says you can get same number. So same procedure of 1 dot, the matrix is also same matrix aij of m cross n. 1 dot a is equal to a. Similarly a dot 1 is equal to a. Hence to prove that multiplication identity law. The sixth property is, for all a comma b belongs to f and x belongs to v, such that ab of x is equal to a of bx. Now ab of x is equal to ab is a scalars, x is a matrix. You can substitute aij of m cross n. Okay, you can multiple the scalars in matrix. So ab of aij of m cross n. We can multiple b scalars. So a into b of aij of m cross n. We can include this two matrix into a into of b of aij m cross n. Can shuffle of these two matrix, these two scalars a of b into aij of m cross n. So here ab of a is equal to a of ba. So hence to prove that associative law. The seventh topic is an a belongs to f and x comma y belongs to v, such that the a of x plus y is equal to ax plus ay is an seventh condition. Seventh condition says a plus a of a plus b is equal to a small a of a plus small b of b. So here small a of a plus b is equal to small a of aij of m cross n plus bij of m cross n. We can take outside of the a of aij plus bij of m cross n. So here adding to this matrix, so only you can write a of aij plus b of bij of m cross n. You can multiple with the scalars a into aij plus a into bij of m cross n. You can split these two matrix a into aij of m cross n plus a into bij of m cross n. So we can get small a of this means that scalars. The scalar into a plus b is equal to small a into a plus small b into b. Hence to prove that left distribution law. The seventh condition is for all a comma b belongs to f and x belongs to v such that a plus of x is equal to ax plus bx. Now a plus b of capital A is equal to a plus b into capital A is a matrix, so aij of m cross n, and capital A you can multiple with the scalars. Yes, so a into aij of m cross n plus b into aij of m cross n. So here you can note that aij of m cross n value is equal to capital A plus b into aij of m cross n value is equal to capital A. So you can write a plus b of a is equal to small a. That means that scalar into a plus scalar into b. So hence to prove that right distribution law. The above 8 conditions are satisfied. So V is a vector space over a field F. Yes. For any doubt for that, any doubt means that comment that box. So now shall we move to problem number 2. Problem number 2 is prove that the set of all polynomial over a field F in a vector space V. You can assume that V is a vector space over a field F in a vector space having a polynomials over a field F. So we can take 3 polynomials u of x and v of x and w of x. These polynomials are satisfies the above 8 conditions means that the vector space over a field F. So we can consider u of x is equal to polynomial a naught plus a1x plus a2x square plus etc. an x power n. The second polynomial v of x is equal to b naught plus b1x plus b2x square plus etc. bn of xn. And third polynomial is equal to c naught plus c1x plus c2x square plus etc. cn x power n. Since u of x, v of x, w of x belongs to v. The first condition is for all x, y belongs to v such that x plus y is equal to y plus x. So here x is equal to u of x, y is equal to v of x, w of x is equal to z. So you can write x is equal to, you can substitute u of x plus y is equal to v of x, you can substitute v of x. So u of x polynomial v is equal to a naught plus a1x plus etc. an x power n plus v of x is equal to b naught plus b1x plus etc. bn x power n. You can shuffle these two polynomials. So you can write first v of x polynomial plus u of x polynomial. The first polynomial is b naught plus b1x plus etc. bn xn plus the first polynomial is, you can write the second term a naught plus a1x plus etc. an x power n. So you can write u of x plus v of x is equal to v of x plus u of x. So hence to prove that commutative law. The second condition, for all x comma y belongs to z belongs to v such that x plus y plus of z equal to x plus of y plus z. So here already know that x is equal to u of x, y is equal to v of x and z equal to w of x. You can write u of x polynomial plus v of x polynomial of w of x. Okay, you can adding first two polynomials a0 plus a1x plus etc. an x power n of b0 plus b1x plus b2x square etc. bn x power n. Okay, plus c0 plus c1 etc. cn x power n. You can, second step is you can split first polynomial a0 plus a1 plus a1x plus etc. an x power n. Next, combining v of x element plus v of x polynomial plus w of x polynomial. So b0 plus b1x plus etc. bn x power n of c0 plus c1x plus etc. cn x power n. You can write u of x plus of v of x plus w of x. So hence to prove that additive associative law. The third condition is for all x belongs to v and 0 belongs to v such that x plus 0 is equal to x and 0 plus x is equal to x. Now u of x plus 0 of x. So zeroth polynomial here. Zeroth polynomial means that 0 plus 0 1 of x plus 0 2 of x square etc. 0 n of x into x power n. Okay. So here adding this two polynomials a0 plus 0 naught plus a1 plus 0 1 of x plus third term is a2 plus 0 2 of x square plus etc. an plus 0 n of x power n. So 0 plus any elements is equal to the same elements. So the same procedure a0 plus a1x plus a2x square plus etc. an x power n. So hence u of x plus 0 of x is equal to u of x. Similarly 0 of x plus u of x is equal to u of x. So hence to prove that additive identity law. So next the fourth condition is x comma minus x belongs to v such that x plus minus x equal to 0 or minus x plus x is equal to 0. The first one you can write u of x plus minus u of x. You can write u of x polynomial is a0 plus a1x plus a2x square etc. an x power n. So next one you can write minus a0 minus a1x minus x minus etc. an x power n. So adding this two polynomial a0 minus a0 plus a1 minus a1x plus etc. an minus an x power n. So here the values is 0. So 0 plus 0x plus 0x square etc. 0x power 1 which is equal to u of minus x plus u of x is equal to 0. Similarly, u of minus x plus u of x is equal to 0. So hence to prove that additive inverse law. The fifth condition is for all x belongs to v and 1 belongs to v such that 1 dot x is equal to x or x dot 1 is equal to x. Now 1 dot u of x equal to 1 into u of x the polynomial a0 plus a1x plus a2x square etc. an x power n. You can multiple with 1 into any polynomial, the value is the same polynomial. So a0 plus a1 x plus a2 x square etc. an x power n. So which is equal to 1 dot u of x is equal to u of x. Similarly, u dot 1 is equal to u of x is equal to similarly u of x into 1 is equal to u of x. Hence to prove that multiplication identity law. So next seventh law is seventh condition. For all a comma b belongs to f and x belongs to v such that a comma b x is equal to a of bx. Now a comma b u of x is equal to ab is an scalars into u of x the polynomial a0 plus a1x plus a2x square plus etc. an x power n. You can multiple with two scalars ab a0 plus ab a1x plus etc. ab an x power n. So taking the common scalars of a in outside. So a of b a0 plus b a1x plus b a2x square etc. b an x power n. So a scalar is already outside. You can take b also outside. So a of b of a0 a1x plus a2x square plus an x power n. You can write a of b u of x. So hence to prove that multiplication associative law. The last law is for all a belongs to f and x comma y belongs to v such that a of x plus y is equal to ax plus ay. So here a of ux plus vx. So a into u of x value is equal to a0 a1 etc. an x power n and v of x the polynomial is b0 b1 x plus etc. bn x power n. You can multiple with a scalar in two polynomials. So a into first polynomial plus a into second polynomial of b0 b1 x plus b2 x square etc. bn x power n. You can write a into the polynomial is u of x plus a into the second polynomial is b of x. So hence to prove that the left distribution law. The last law is an a comma b belongs to v and x belongs to v such that a plus b of x is equal to ax plus bx. Now you can write a plus b of u is equal to a into u of x plus u of x. Hence to prove that right distribution law. So we can verify every set of polynomial over a field in vector space V. Yes, in this topic you can discuss two problems. The two problem is very important. The first problem is an set of matrix set of matrix A matrix, B matrix, C matrix in a vector space over a field F. The second problem is an set of polynomial over a field in a vector space V. Okay, the second topic is an subspace. The subspace definition is let V be a vector space over a field F on a non-empty subspace and a non-empty subset W of V is called subspace of V. If V1, V2 belongs to V and alpha comma beta belongs to F, which is implies that alpha V1 plus beta V2 W2 belongs to W. So you can clearly note the diagram. V is a vector space over a field F and W is a subspace of V. Yes, you can understand V is a vector space over a field F and W is a subspace. The subspace having the elements in W1 and W2. The two elements and alpha and beta in vectors alpha and beta in two scalars in F. So which is implies that alpha W1 plus beta W2 also belonging to in a same subspace is called subspace. Okay, you can image V is a vector space over a field F and W is a subspace of V. A subspace having the elements W1 and W2 and alpha and beta two scalars in F, which is implies that alpha W1 plus beta W2 belongs to W. Satisfies these conditions means that given set of elements in a subspace of W. Problem number 1. Prove that W of A, 0, 0 such that A belongs to F is a subspace of R cube. So we can prove that W is a set of elements. So A is a scalar in a subspace of R cube. You can consider W1 is equal to A, 0, 0 and W2 is equal to B, 0, 0. Since W1, W2 belongs to capital W and A, B belongs to F. It's a given statement. We have to next to prove that W is a subspace of the vector space of R cube. By using subspace definition, it says that W1, W2 belongs to W and alpha, beta belongs to F, which is implies that alpha W1 plus beta W2 belongs to capital W. So the substituting this formula, alpha W1 value is equal to A, 0, 0 plus beta into W2 value is equal to B, 0, 0. So adding these two elements alpha A plus beta B, 0 plus 0, 0 plus 0. Hence the value is equal to alpha A plus beta B, 0, 0. So here also three elements. So belongs to R cube. Hence to prove that W is a subspace of R cube. It's an 2 mark question. Second one is an important 8 mark question. Prove that the intersection of two subspace of a vector space V in a subspace of V. Okay, here prove that intersection of two subspace of a vector space V in a subspace of V. Can understand this problem? So clearly you can note that, can write the diagram. V is a vector space over a field F. Yes. Here V1 intersection of V2. The two elements also belonging to in the subspace of V. Can understand? Here V is a vector space in the sum. V also a subspace and over a field F. Can here you can note that the idea in this problem. Yes. So first you can V is a vector space over a field F and W is a subspace of E. So here W is means that V. So V is a subspace over a W is a subspace of V. So here V1 intersection V2 also same in the subspace. Yes, we have to prove that one by one. First one, let us consider V1 and V2 are two subspace of the vector space V. We can take A comma B belongs to V1 and A comma B belongs to V2. We have to prove that V1 intersection V2 is a subspace of the vector space V. By using subspace definition, W1 and W2 belongs to W1 and W2 belongs to W and alpha comma beta belongs to F, which is implies that alpha W1 plus beta W2 belongs to capital W. Since V1 comma V2 belongs to V and alpha comma beta belongs to F, which is implies that alpha V1 plus beta V2 belongs to alpha V2 belongs to V1 intersection V2. You can note that in this line, since V1 and V2 belongs to V, is an definition. The second line is an definition. W1 and W2 belongs to W and alpha comma beta belongs to F, which is implies that alpha W1 plus beta W2 belongs to W. So since we here V1 and V2 is an subspace belongs to V. Okay, V1 and V2 two vectors V1 and V2 belongs to V and alpha comma beta belongs to F, which is implies that the same definition you can write alpha V1 plus beta V2 belongs to V1 intersection V2. So here you can write belongs to capital V because is a subspace of capital V. Okay. So we can take A comma B belongs to V1 and alpha comma beta belongs to F, which is implies that V1 is a subspace of alpha A plus beta B belongs to V. Then first equation. Second equation is we can take A comma B belongs to F and A comma B belongs to V2, which is implies that V2 is a subspace of alpha A plus beta B belongs to V2. So from equation number 1 and 2 implies that alpha A plus beta B belongs to V1 intersection V2. So hence to prove that intersection of two subspace of the vector space V is a subspace of V. You can understand? Hence to prove that intersection of two subspace of a vector space V is a subspace of V. So here V is a subspace and V1 and V2 is a subspace, and also to prove that V1 intersection and V2 is a subspace of the vector space V. Yes, is an important 7 more question. Next one 2 more question. Prove that union of two subspace of a vector space need not be a subspace. So we can assume that capital A is equal to set of all A comma 0 such that A belongs to R, and capital B is equal to set of all 0 comma B comma 0 such that B belongs to R, since AB belongs to R power 3. So we can take A equal to 1, B equal to 1, since 1 comma 0 belongs to capital A and 0 comma 1 comma 0 belongs to capital B. We have to prove that union of two subspace of the vector space need not be a subspace. So which is implies that 1 comma 0 comma 0 union of 0 comma 1 comma 0 does not belonging to A union of B. So here you can clearly note that we can assuming the elements is also A comma 0 comma 0. The second subspace is at second subspace B is equal to 0 comma 1 comma 0. The elements is not equal. So the union of two set of elements also does not belonging to A union of B. So hence to prove that union of two subspace does not belonging to the vector space. The third topic is linear independent and dependent. So definition of linear dependent: a subset S of a vector space V is called linearly dependent if there exists a finite number of distinct vectors. So here the definition of linearly dependent: the linearly dependent means that a subset of S of a vector space V is called linearly dependent. There exists a finite number of distinct vectors u1, u2, etc. un in S and the scalars a1, a2, etc. an or not all are 0. So here a1, u1 plus a2, u2 plus etc. an, un. So clearly you can note that a subset S V is a vector space and subset F there exist a distinct vectors u1, u2, etc. un and the scalars a1, a2, etc. an and the scale and such that a1, u1 plus etc. an, un is not equal to 0. You can note that V is a vector space S and S is a subset. A subset having the distinct vectors u1 to un and scalars a1 to an and such which is implies that a1 u1 plus etc. an un as not equal to 0 is linearly dependent definition. Suppose linearly independent means that V is a vector space, S is a subset having the vectors u1, u2, etc. u1 and scalars a1, a2, etc. an which implies that a1 u1 plus a2 u2 plus etc. an un is equal to 0. So here the scalars are equal to 0. This means that linearly independent. Yes, the scalars are equal to 0 means that linearly independent and scalars are not equal to 0 means that linearly dependent. So you can difference between linearly independent and dependent. Yes, so linearly independent means that the scalars are equal to 0. Linearly dependence means that the scalars are not equal to 0. So the problem, check the following equation is linearly independent or dependent. The problem is u1 is equal to 4 comma 2 comma 1 and u2 is equal to 2 comma 6 comma minus 5 and u3 is equal to 1 comma minus 2 comma 3. Solution: given u1 is equal to 4 comma 2 comma 1 and u2 is equal to 2 comma 6 comma minus 5 and u3 is equal to 1 comma minus 2 comma 3. We have to choose the equation of linearly. We have to find equation of linearly independent and dependent. So by using definition of linearly independent definitions, a1 u1 plus a2 u2 plus an u1 etc. is, you can clearly note that the given given statement, given vectors are linearly independent or dependent. So only you can using linearly independent definitions. So thus means that a1 u1 plus a2 u2 plus etc. an un. So here given three vectors only. So you can write a1 u1 plus a2 u2 plus a3 u3 is equal to 0. Okay, so you can substitute u1 u2 u3 vectors and multiple with scalars. So a1 4 comma a1 2 comma a1 1 plus a2 2 comma a2 6 comma a2 minus 5, a3 1 comma minus a3 2 comma minus a3 3 equal to 0. You can convert the equations form. So you can adding first elements. So 4a1 plus 2a2 plus 1a3 is equal to 0. 2a1 plus 6a2 minus 2a3 is equal to 0. The third one, a1 minus a2 plus 3a3 is equal to 0. So you can solve any two equation. You can using solve equation number 1 and 2. The first equation is, can write 4a1 plus 2a2 plus a3 is equal to 0. And the second equation multiple with 2. So 4a1 plus 12a2 minus 4a3 is equal to 0. Subtraction of these two equation, a1 getting cancelled. Yes. Then a2 value is minus 10 and a3 value is equal to plus 5 is equal to 0. So here 2a2 is equal to a3. Simplifying this term, 2a2 is equal to a3. And solve equation number 2 and 3. You can write two equations in the same. 2a1 plus 6a2 minus 2a3 is equal to 0. And third equation multiple with 2. So 2a1 minus 10a2 plus 6a3 is equal to 0. Subtraction of these two equations, 16a2 minus 8a3 is equal to 0. So you can simplifying this term, 2a2 is equal to a3. So here equation number 4 and 5 are same. So only we can take a3 is equal to 1. So substitute. This is a procedure. The equation 4 and 5 is same. So only we can put a3 or a2 is equal to 1. So here a2 is equal to 1 means that a3 value is equal to 2. So substitute a2 is equal to 1 comma a3 is equal to 2 in equation number 1. So 4a1 plus 2 is equal to 0. So here 4a1 plus 4 is equal to 0. Simplifying in this term, a1 is equal to minus 4. So here scalars, a1 is equal to minus 4, a2 is equal to 1, a3 is equal to 2. The scalars are not equal to 0. So given vectors are linearly dependent. Yes. So second problem is, for what value of C or the vectors minus 1 comma 0 comma minus 1, second vector 2 comma 1 comma 2 and third vectors 1 comma 1 comma c in r power 3 is linearly dependent. So in this problem the vectors are linearly dependent. You can find out in c value. Yes. So we can take the first vector is u1, second vector is u2 and third vector is u3. You can find the value of c. So using definition of linearly independent definition, a1 a2 etc. A1 u1 plus a2 u2 plus etc. an un is equal to 0. So here the problem is given 3 vectors only. You can write a1 u1 up to a3 u3 is equal to 0. You can substitute u1 u2 u3 vectors and multiple with the scalars in a1 plus a2 the scalars plus a3 the scalars equal to 0. You can consider the equation minus a1 plus 2a2 plus a3 is equal to 0. Second equation is 0 a1 plus a2 plus a3 is equal to 0. The third equation is minus a1 plus 2a2 plus ca3 is equal to 0. Solve equation number 1 and 3. So equation solved on 1 and 3 means that you can subtract this type of these two equation, a1 getting cancelled and a2 getting cancelled also. Then a3 minus ca3 is equal to 0. Here minus ca3 is taking outside means that a3 is equal to ca3. So here a3 getting cancelled, c is equal to 1. So hence c's value is equal to 1. Okay. So next problem number 3 is determine the following sets are linearly independent or dependent. So here also given 4 vectors or 2 vectors. So sorry, problem number 1 is 2 vectors, problem number 2 is the subdivisions. So problem number 2 also, second option is 2 vectors. The first you can write problem number problem number 1 given u1 2 minus 1 4 and second set of vectors minus 1 1 2 minus 4. We can take u1 is equal to 1 2 minus 1 4, u2 is equal to minus 1 1 2 minus 4. To find the vectors are linearly independent or dependent. So by using definition of linearly independent and dependent definition, a1 u1 plus a2 u2 plus etc. an un is equal to 0. So here given only a 2 vectors. So a1 into u1 value 1 minus 2 minus 1 4 plus a2 into second vectors minus 1 1 2 minus 4 equal to 0. Can multiple with 2 scalars a1 minus 2a1 minus a1 4a1 plus you can multiply with second scalar minus a2 2 into a2 minus 4a2 which is equal to 0. So adding with 2 set of vectors a1 minus a2 minus 2a1 plus a2. The second one minus a1 plus 2a2 4a1 minus a2 is equal to 0. Can convert it to the equation form a1 minus a2 is equal to 0 minus 2a1 plus a2 is equal to 0 minus a1 plus 2a2 is equal to 0, 4a1 minus 4a2 is equal to 0. Solve equation number 1 and 4. Equation number 1 and 4 is same because a1 first equation is a1 minus a2. Second fourth equation can divide in the fourth term a1 minus a2. From equation number 1 a1 is equal to a2. So here a1 is equal to a2 means that substitute a1 is equal to a2 in equation number 2. So minus 2 into a2 plus a2 is equal to 0. So minus 2a2 is equal to minus a2. So here minus a2 is equal to 0, a2 is equal to 0, substitute a2 is equal to 0 in equation number 1. So a2 and a1 is equal to 0. So here the scalars are equal to 0. Therefore given vectors are linearly independent. Yes. Given vectors are linearly independent. So in this linearly independent dependent means that the scalars are equal to 0 means that linearly independent. The scalars are not equal to 0 means linearly dependent. Yes. So for any doubt for this linearly independent dependent means that comment that YouTube channel. Thank you.